In this video, we're going to talk about how to make the Wein bridge oscillator circuit using the 741 op-amp device. So here's a diagram of that device. Pins 1, 5, and 8 will not be used in the circuit. 1 and 5 are the offset nulls. Pin 2 is the inverting input. 3 is the non-inverting input. Pins 4 and 7 are for the supply voltages, and 6 is the output. Now you might be wondering how to implement negative V and positive V in the circuit. In this case, here's what you can do. So you could use two batteries in series with each other. And we're going to use two 9-volt batteries. So this is the positive side, and then the other part is the negative side. At the center will be the ground. So the ground will be set at a reference of 0 volts. The top part is positive 9V. We're going to connect that to pin 7. The bottom part is negative 9V with respect to the ground, and so that will be connected to pin 4. So let's begin by drawing the Wein bridge oscillator circuit. So we're going to begin by drawing a triangle with the two inputs. So attached to input 2, that is the inverting input, we're going to have R4. Also attached to pin 2 will be a feedback resistor, and we're going to call that R3. R3 controls the gain of the circuit. And we're going to connect that to the output, pin 6. Now attached to pin 3, which is the non-inverting input, we're going to have a resistor, R1, and a capacitor, C1, both of which goes to ground. R4 also goes to ground. So let's call this R1 and C1. Next, we're going to have another capacitor and a resistor, which connects to pin 3 of the op-amp and pin 6, the output. So this is going to be C2 and R2. So that's the basic design of the Wein bridge oscillator. So the gain of this circuit is R3 divided by R4. R3 provides negative feedback to the inverting input. And so as you decrease the value of R3, the gain decreases. So thus it allows you to control the gain of the circuit. Now according to most textbooks, in order for the oscillations to be sustained, you want a gain of around 3. If the gain is too low, the oscillations will fizzle out. If it's too high, it can go to saturation and even distortion. So under ideal circumstances, the gain should be about 3. I've actually built a circuit with a gain that is a little bit less than 3, but it worked. But according to most textbooks, this is the value that you want. Now the frequency of the circuit is dependent on R2 and R1. To make the circuit work, you want to set R1 equal to R2, and you want to set C1 equal to C2. If these values are off, you may not get a nice sine wave. You might get a spiked waveform or some distorted signal. But if you want to get a good sine wave for this circuit, you want to set R1 equal to R2 and C1 equal to C2. So we're going to call R1 and R2 R, C1 and C2 C. The frequency of the oscillations can be calculated using this formula. It's 1 over 2 pi RC. So what you need to understand is this. The frequency is inversely related to R and C. As you increase the value of R, the frequency goes down. And as you increase the value of C, the frequency goes down as well. Now it might be wise to use a potentiometer for R1 and R2. But you want to use a gang potentiometer so that R1 and R2 can have the same value. You could also use a potentiometer for R3. So thus you can adjust the gain until you get a nice sine wave at the output. Because you don't always get a pure sine wave at the output for different values of R and C. So sometimes you have to adjust it until oscillations begin to occur. So here are some values that I've used when I tested a circuit. So I set R3 equal to 68K and R4 to 33K. And in this case, R3 is a little bit more than twice the value of R4. It's not 3 times as much. It's a little bit over 2. But when I tried it, it worked. And don't forget to set pin 7 to positive 9 volts. And also pin 4 to negative 9 volts. I forgot to put that in there. So R1 and R2, I set it to 1K. I used two 1 kilo ohm resistors for those two values. And for C1 and C2, I used a 0.1 microfarad capacitor. And for this particular circuit, I got a nice sine wave with a peak voltage of around 600 millivolts. The measured frequency that I got was 1.585 kilohertz, which is actually pretty close to the theoretical frequency. Let's calculate the theoretical frequency using this formula. So we have 1 over 2 pi. R is 1 kilo ohm or 1,000 ohms. C is 0.1 microfarads or 0.1 times 10 to the minus 6 farads. So if you plug this in, you should get a theoretical frequency of 1591.5 hertz, which is 1.592 if you round it kilohertz. As you can see, that's very close to the measured frequency of 1.585 kilohertz. So this circuit works. The only difference is you just need to, the only issue is you need to fine tune it until you have the right values where the circuit begins to oscillate. And you want to make sure that R1 and R2 are the same. I've tried this circuit where R1 and R2 are different. In one example where R2 was 1 kilo ohm, but R1 was set to 2.2 kilo ohms, C1 and C2 were the same, 0.1 microfarads, I got a waveform that looked like this. It was like a spiked waveform. My drawing's not perfect, but it was something like that. Not purely a triangle waveform, but it looked something like that. The idea is that if R1 and R2 are not the same, you're not going to get a pure sine wave. You may get a spike waveform or a triangular waveform or something distorted. So just keep that in mind. Also, even if you set R1 equal to R2, you need to find the appropriate R value that corresponds to the capacitance value that you're using. Because when I use C1 and C2 as 0.1 microfarads, and I had both R1 and R2 set to 8.2 kilo ohms, I didn't get a nice sine wave. Instead, I got something distorted, but not necessarily like a triangular waveform. I got something that looked like this. It wasn't a perfect sine wave, but it was better than the other waveform. It looks something like that. In either case, it appears more of a sine wave than the other spike waveform that I had before. So if you're going to design a circuit, make sure that R1 is set to R2 that they're equal to each other, and that C1 is equal to C2. And then R3 should be about 3 times this R4. You might have to vary that, maybe try a little bit more, a little less, until it works. So it might be wise to use a potentiometer here and adjust it accordingly until oscillations begin. So that's it for this video. Now you know how to design the Wein bridge oscillator circuit. Thanks for watching.